All right, we'll go ahead and get started. Couple of quick things to point out that I wanted to make sure to address real quick. So first one is I said I would be taping these lectures. So if you are wondering where they're at, the easiest way to get to them is just this link to here in Blackboard, and that should just pull this up. And I'm going to be separating them out by like class of the day too, so it's the same information, but if you want to listen to things that I've said in this particular class section, they're the 1 p.m. ones. So that's there. And then the second thing I wanted to point out real quick was, I know some people have actually already been trying it, but the homework for Wednesday is a quote-unquote quiz. I'm not grading you on correctness, I'm grading you on just doing it, participating. So what it's going to hit on are basic structures of, or basic structural pieces of microorganisms. So take a look at that ahead of time. This one's more of an individual assignment than it is a group one, but don't feel like you have to do it in isolation. You can work with a partner on it. It's set up so that you can revisit it as frequently as you want to, and I've already gotten a couple of questions like there's one where like there's two letters, C and D. They both look like they're pointing to the middle of nowhere, and I just put a quick note like C is pointing to a red dot, D is pointing to the middle of nowhere. So take a look at that. Again, not grading on correctness, I'm grading simply on have you taken the time to do it. Okay, so that is for Wednesday, and then reminder that for lab on Wednesday, the microscope, make sure to, again, it's just a picture out of the lab manual, print that out, fill out or make sure you identify the parts of the microscope, and then just a quick phrase or description of each of those parts as well, so that we have a starting place for our conversation. That's going to be due in lab on Wednesday. So you said your 10 o'clock lab? Or no, your afternoon. So 1 o'clock or 2 o'clock, when you show up to lab, just hand it in to John right away. Okay? So at lab time. Any questions? How many people had trouble with the images? Good Lord. Okay. Everyone.
You just had to click on it and then.
Well, yeah. So that's why I put up the backup, because I think in retrospect, as I was trying to figure out the issue today, I think I now know what it is, and it was the wrong file format. Anyway, speaking of those, why don't we start off by breaking into our groups for a few minutes? What I want to do is just take 10 minutes and address 3 things here. I made sure to look at everybody's by this morning, so what I'd like you to do, if I've left any questions or comments, address those first. So for some, like probably the most common question, actually, I didn't do it many times, but the most common one was, in prokaryotes, is there a nucleus?
No.
Thank you. All right. So if you put that DNA and RNA are found in the nucleus, get rid of that, because in prokaryotes, no nuclei. Okay. Once you address those questions, or if you don't have any in there, what I want you to do is work a little bit deeper. Add one piece of additional information to each of them. So for example, not every single cell, but to each of the building blocks. So give me one additional piece about amino acids. Give me one additional piece of information about carbohydrates or monosaccharides, fatty acids, and then nucleotides. And do this as your group. And then the last one is I'm going to draw a molecule up on the board. And just to make sure, to see if everybody's on the same page, what I want you to do is identify what's the molecular formula of it. I want to make sure that folks can follow along with the shorthand that I'm going to use for drawing molecules, because for anybody who's taken organic, it's a whole lot easier to not have to write carbon for every single carbon. So break into your groups, and don't feel like you have to take everything with you, because Assume yes. Assume that you are a group of 3. I have not received an answer on that, though I've been asking about it, but I am running under the assumption that, yeah. Yeah. All right. What should I draw?
And then we have to add like something to I thought it was true question.
So what's the question?
So the monomer of like the
you can say they're saturated.
Technically, there's no polymer, but what we really talk about are how fatty acids break up
Question on top of it.
So then, why make sure sterols in there as like part of the group, but like not?
Because just like one thing that kind of groups all of those together is that they are
There's like a
so mostly non-polar bonds. I think that's why they grow.
It's like there's like a double difference. Like the 2 lines.
Don't worry so much about the distinction in analysis. We really won't talk about it. Sure. Add an extra note. So like. Alright, so
that's the monomer. There's
that you guys
We're saturated by having prior to like. So it depends if I just think now like has it like this shape. I would do carbon ions. I was gonna say they go down to according to the carbon.
I don't either. It's like not easier. Like mine is super easy on my computer, but I don't know how to do it. So.
Glyceride is just open this up. So there's hydroxyl group,
Yeah, I realized that.
carboxyl group, just a hydroxyl group and
Say there.
oh wait, is C double bonded to carb?
A C double bonded to an always carbonyl, but if you've got like that and then an OH group off of it, we call it a carboxyl. So like all of this right here.
Which is carbonyl
Just 20 common amino
and hydroxyl combined.
Is there a name for that?
Just some general features of the different building blocks. This right here, what is this building block? Where would you categorize it? In terms of the 4 that we've talked about, is it an amino acid? Is it a monosaccharide? Is it a nucleotide? Or is it a fatty acid? It's a fatty acid. So how do we know? One way is if you want to, you can memorize. But memorization is only going to get you so far. Another thing might be to start thinking about what are the trends? What are things that all fatty acids have? So what are the characteristics of this molecule, as we can see up on the board? What functional group is circled? That's a carboxyl. Every single fatty acid has a carboxyl group. What about the rest of it? Nothing's labeled, but what's there? Carbons and hydrogens. Sometimes folks use the word hydrocarbons to refer to fatty acids or lipids, for example. And so all fatty acids have a hydrocarbon tail. They've got a carboxylic head group. And if you can identify those two features, you know you're looking at a fatty acid. So rather than trying to imagine or memorize this exact photo, rather you're thinking about the trends of what you would expect to find here. Okay. This one, how many oxygens? That should be pretty self-explanatory. 2. Okay. How many carbons? What do we got? 1 here, 2, 3, 4, 5, 6, 7. Am I missing any? I think that's right. And then what about hydrogens? And remember, how many bonds do carbons make? Good. So anything where we don't have a line drawn to a carbon, we assume is a hydrogen. So there's none here, because that carbon's already bonded to an oxygen, double bonded to another oxygen. So that's 3 bonds total and another carbon. So we got 1 hydrogen, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. Because these 2 carbons here have double bonds. So they're already making 1, 2, 3 bonds with other carbons. So 1 filled in with hydrogen. Okay. How do I know that? 1 full year of organic chemistry. And that's about all I remember. Now, in all honesty, I'm trying to give you guys just a kind of really quick crash course. And again, carbon makes 4 bonds. Even if it's a double bond, that counts as 2. So the easiest thing usually is to go through and count first how many bonds are those carbons making, and then just take 4, subtract that number of bonds it's making, and the rest of them are hydrogens. Okay. Kaylee.
How come those ones
Well, how many bonds? So you're talking about these 2 versus these ones? So these 2 right here, this is a double bond. These 2 lines represent a double bond. And so they're both making 1, 2 with each other, and then they've got a third one that they're each making, a third carbon that they're both making bonds to. So that leaves 1 available spot for binding still. And that'll be to a hydrogen. Okay. Now that I've drawn all over this one, is this a saturated or unsaturated fatty acid? Unsaturated, right? Saturated would have just single bonds in that hydrocarbon tail. Cis or trans? And how do we actually know? It is a cis. What's cis mean? If you were, so what's another word for cis? Or what's another word for trans? If something is trans, it's opposite, right? Cis means same. So what are we actually referring to? We're actually referring to the carbons adjacent to that double bond. So what I end up doing is if you take these double bonds, draw a line down it. Okay? These are the adjacent carbons. Are they on the same side or opposite sides? Same. Therefore, it's cis. If this one were up here, so you had a shape like this, that would be trans. Okay? So it's only what's around a double bond, and again, referring to those adjacent carbons. Are they on the same side or opposite sides? We'll come back to that cis conformation in a few minutes. Okay? Questions on fatty acids? Functional groups in amino acids. What do we have? All amino acids have what? Amino group, NH2, and a carboxyl group. Some people said there's an R group. Yep, that's true. That R means any of 20 different side chains made up of carbons, oxygens, hydrogens, nitrogens, and sulfur. All right. Name comes from the fact that you've got an amino group and an acid or a carboxylic acid group. And then how do these actually, when these bond together, if we have two amino acids next to each other and we, what instrument or machine in the cell actually bonds these together? In other words, what part of the cell actually makes proteins? Ribosome makes them, and we'll cover that on Wednesday. What kind of reaction occurs? Dehydration, meaning what? Loss of water. Okay, we'll come back to that in a second as well. We'll draw that out. I want to get rid of this. There we go. Or not. Okay, fine. Oh, that's why. Okay, let's take a look at these real quick. These are monosaccharides, aka simple sugars, aka carbohydrates. Again, what are some key features here? So again, if you're looking at the trends, what would you be looking for if you were trying to identify a monosaccharide? Well, what are the basic pieces of a sugar? Good. Carbon, hydrogen, and oxygen. What's true about, and then what functional groups do we have here, largely? Carboxyl, if we're talking about the linear form, typically in cytoplasm, these are going to be in a ringed form, so hydroxyl will be most abundant. What about the ratio of carbon to hydrogen to oxygen? It is. It's 1 to 2 to 1, unless you start getting disaccharides or trisaccharides, and that ratio starts to break down because, again, what drives those together are dehydration reactions. And so you start to lose an oxygen and 2 hydrogens each time those bonds form. So key characteristics here you might be looking for, that 1 to 2 to 1 ratio, bunches of hydroxyls. And then the last one, nucleotides. All nucleotides have what 3 basic parts? And I'm not saying functional groups here, but what 3 basic parts? Phosphate? A sugar. And the sugar can be ribose or deoxyribose. We'll talk more about that later on in the semester. What's the last piece? Nitrogenous base. So you're looking for those 3 basic structural pieces to determine if it's a nucleotide or not. Okay. I want to go back to functional groups real quick and just reiterate, there's only 4 of them that I want you to know. Now for this, there's no other way to get around it than just to memorize them. NH2, we've defined as our amino. We've talked about this. I'm just going to draw R there. This is our carboxyl, or carboxylic acid. OH is our hydroxyl. And then the last one that I would like you to remember, and this one is fairly easy given the fact that there's a phosphorus in it. This is what? Oh gosh, the writing's getting really bad. What is this one? Sarah? Phosphate, perfect. There's one other one I may bring up from time to time. It's a CH3 group, which is known as a methyl. I'm not expecting you to memorize that right now. Okay. If you were to look at these 4, the phosphate, the amino, the carboxyl, and the hydroxyl, think about our conversation on Friday. We talked a lot about bonding. what's true about the bonds that you observe in these 4 functional groups? Are they polar, ionic, or I'm sorry, are they covalent or ionic is what I meant to ask. They're covalent bonds. The next question is, for example, that OH bond or the nitrogen-hydrogen. Are those polar or nonpolar bonds? And if you need the electronegativity values, oxygen is 3.5, hydrogen's 2.1, nitrogen is 3.0. So based on the calculations that we talked about on Friday, are those bonds polar or nonpolar? They're polar bonds. In other words, what we know about these functional groups is every single one of them is reactive. And that is really important to production of energy, to metabolism, to building molecules in general, taking us from these monomeric forms to these polymeric forms. Okay. CH3, on the other hand, nonpolar. And so CH3, that methyl group, isn't as reactive, and that becomes really important when we talk about things like gene expression. Methyl groups are oftentimes used as a way to like shut off or quiet DNA from expressing genes, whereas these other ones can turn on gene expression. All right. Let's real quick. So I'm going to go to our amino acids. All right. So let's walk through one dehydration reaction. Oh, yeah. Thanks, Sid. You guys can all go back at this point to your spots if you want to. Nope. Yeah. All right. I'm going to draw out 2 amino acids. And amino acids get bonded together in a very repeatable pattern. We always have bonds occurring between one of the hydrogens on the amino group and the hydroxyl from the carboxyl group of another amino acid. Synthesis of building blocks, or taking those building blocks and making macromolecules out of them, is based on these dehydration reactions. And in every single one, water is going to fall out of solution at some point. So in this case here, we have the OH from the carboxyl group, the hydrogen from the amino group. Those will get removed as water. And I'm just going to erase them now. And then we get a bond between this carbon and that nitrogen. And this is actually known as a peptide bond. And the only reason why I bring that up is because the other name for a protein is a polypeptide. Okay, repeated peptide bonds over and over and over again. Now, if you take a look at this, what this shows you is that regardless of the size of these polypeptides, there's always going to be a free amino group at one end. There's always going to be a free carboxyl group at the other end. And when we read a protein sequence, we're always reading from the amino to the carboxy sequence. That's what we call the primary structure. It's just the amino acid sequence. Okay. Any questions on that dehydration reaction, or just the premise of it? What's the opposite of dehydration reactions? Hydrolysis. Water added back in to break them. Allie.
I have a question. Is the oxygen double bonded to a carbon?
It is.
Okay.
Yeah. Again, that carbon is unlabeled here, but that is a double bond to a carbon.
So
Absolutely.
There's just one carbon in that.
So there's a carbon here, and there's actually this little, where that intersects is a carbon too. Yeah, we call that the central carbon on these amino acids. Great question. All right, I'm going to have you guys practice. So I'll erase this. Let's say that we have a glycerol molecule. So glycerol has 3 carbons at the middle of each of these, or at the cross section of each of these lines. Hydrogens, and then hydroxyl groups. And fatty acids will bond to these glycerol molecules to form phospholipids or triglycerides. What I want you to do is, given what we've just talked about, and you may not know the answer to this, and that's okay. What's going to happen here? Where does the dehydration reaction occur to create at least one of these glycerol fatty acid bonds? Okay? So first identify your water. First identify where you're going to get your water from. I'll give you a couple of minutes to fight with this.
I'm not sure, but I think like one of the hydrogen connects
Huh?
to the OH, you know, fatty acid. Like the, like at each one.
Which hydrogen? No, there's any.
The one on the end.
Okay. Think about that for a minute. Carbon-hydrogen bonds, are they reactive? Or are they... So think about, what if we said that if a bond is reactive, or let me try this a different way. Carbon-hydrogen bond, polar or not polar?
They're polar.
Are they?
No, they're non-polar, so they're non-reactive.
Good. So you need to pick a different hydrogen to work with.
I got it back up.
Okay. Yeah. So a couple of people already are trying to figure out which of these hydrogens on this glycerol, right? Where are you going to get your OH from? Probably from the carboxyl group, right? That's one source of OH, and we've already talked about that as being a source. And in every single dehydration reaction we look at, there is an OH group, a hydroxyl somewhere, that will be involved in the reaction. So the question becomes, you've got hydrogens, you've got, 8 of them total on this glycerol molecule? Which one do you pick? Let's simplify this. There's really only 2 types of hydrogen molecules on or 2 types of hydrogen atoms on this glycerol molecule. There are these ones, hydrogen bound to a carbon, or these ones, hydrogen bound to an oxygen. What is true about, or what are the characteristics of hydrogen bound to carbon versus the characteristics of a hydrogen bound to an oxygen? That was one. Zach?
Yeah, like just the polarity of it, it's going to be opposite.
Good. So which one is nonpolar? Good. The CH is nonpolar. Think nonpolar means not reactive. Okay? What you need here are partial positive and partial negative charges. And actually, we get some hydrogen bonding even before the reaction takes place between this OH group on the fatty acid and between those OH groups on the glycerol molecule. So already you're getting some interaction there. And what really happens is this partial positive on that oxygen actually will end up stealing that hydrogen from glycerol. That falls out of solution, and then what you're left with, instead of drawing this, I'll just go ahead to the slides. You're left with something like this, where you've got the remainder of this glycerol molecule. Note there's an oxygen remaining from that glycerol, bound to the remainder of that carboxyl group from the from the fatty acid. Okay. Am I expecting you to be able to draw this?
No.
I haven't decided. I guess the reason why I point this out is because the rules of these dehydration reactions are transferable across all the different building blocks. You need a reactive hydrogen, you need a reactive OH group. And if you can identify those, then you should be able to get pretty darn close as to what that final molecule is going to look like. Okay? We'll stop with just these ones. We'll come back to nucleotides way down the road. Glucose or monosaccharides, I've got an image of those as well. You're basically just looking for any two old hydroxyl groups. Okay. Questions on that premise of hydrolysis, dehydration? Sid?
So that hydrogen-oxygen bond, is that polar or no?
It is a polar bond, yeah. And again, it's the electronegativity difference between the two of them that help to define that as a polar bond. Yep. Other questions? Okay. With the time that we have left, let me see where I want to go with this. There's a couple of questions that we could address. I'm just trying to figure out which one's the best one. Okay, I think where I want to go is here. So in this image, what you see is a phospholipid, which are used to make what? Membrane, perfect. Or if you were talking eukaryotes, you would say organelle membranes as well. But in terms of bacteria, cell membrane. We'll talk about some bacterial species that actually have two membrane systems, a cell membrane and then an outer membrane. So common characteristics, two fatty acid tails, glycerol, phosphate, sometimes addition onto the phosphate. And what's being shown here is what might these membranes look like with saturated fatty acid tails versus ones that maybe have some cis unsaturated fatty acid tails. If you could describe what the difference is between those two images, what's one way to describe it? Go ahead, Zach.
For the unsaturated, it'll be fluid. So it would be, so that's like what the membranes are doing.
And maybe the way to say it would be, it's going to at least be more fluid than the saturated at the same temperature, right? Because what do those cis fatty acid tails do? They create some space, right? So imagine if, like I said, all right, everybody's going to go into that corner right there. Everybody stand up and go into that corner. And we all stood like this. We'd probably all fit, right? But it would be kind of hard to move through because we'd be packed pretty tightly. But if we all stood with our arms out, mimicking a cis unsaturated fatty acid, we probably wouldn't all be able to fit in that area, but we'd likely be able to move around more easily, right? And so what cis unsaturated fatty acids do is they create spacing between those phospholipids, thereby increasing fluidity of the membrane. And why is this important? Well, it's important for cell homeostasis. Every single cell has to have the ability of gases to move in and out of the cell for some nutrients to passively diffuse through that membrane. It's just an inherent part that is important to life. One of the things that microorganisms can do, and this is true in eukaryotes as well, but microorganisms, I like to bring this up because bacteria can't regulate body temperature, right? They are single-celled organisms. So think of this example here. Let's say that we've got one organism, one bacterium that lives in the Arctic. Not Arctic. And then another one that we'll say like it lives in Cuba. Which one of those two is going to have a higher percentage of cis unsaturated fatty acids? Okay. I'll let you mull on it because the follow-up question is justify your answer. Tell me why. And then because does not work. All right, so take a couple of minutes. Feel free to talk it over with somebody else. Which one will have a higher percentage of cis unsaturated fatty acids and why? And let me add one more caveat to this, maybe to help as well. Let's say that the fluidity of the membrane is the same. So let's say that nutrients move in and out of these two at equal rates. Okay? Which one would have more cis unsaturated? So saturated aren't cis or trans because they don't have double bonds, right? The cis or trans really only refers to in cases where there's double bonds. And this isn't something I really brought up, but double bonds cannot be turned, right? But single bonds can rotate. And so at one moment, you could have two carbons in the cis conformation and then right after in the trans. But with a double bond, that can't move. And so those adjacent carbons are always either in the cis or always in the trans conformation. So those cis and trans terms only refer to unsaturated. Now,
How do you tell the difference?
so it comes back to where are those two carbons. So for example, let's say I have if you look at this carbon and this carbon, so the two that are just outside of that. Oh, we did that. Down the middle.
Why didn't you ask me?
Same side or opposite side?
But I was like, okay, I have to get ready, and then
This
I
one here and this
right
one.
here, take the
Are they on the
bus,
same
or
side of this line?
but
So this would be a,
I'm
if
Friday,
you wanted a cis,
and
and in nature, we only find actually cis. Trans is a product of chemistry.
Okay, so we're mainly working with cis.
Yes. All right. So what's the answer? Cuba or the Arctic? Anybody want to take a guess? Who says Cuba? Raise of hands. Who says Arctic? Raise of hands. Who says the hell with it? Why should I care? All the hands should go down now. All right. It's about permeability, okay? A cell tries to maintain a constant amount of permeability. So when temperatures cool, imagine you have, for example, butter. Butter at room temperature, solid or liquid? Solid. Okay, good. You warm it up in the microwave, it becomes liquid. Good. Butter is made out of saturated fats. Okay? So temperature increases, it becomes liquid, fluidity increases as well. Okay? As temperature of that butter as it cools again, it starts to solidify. And the permeability or the movement, that fluidity, decreases. So, if you have an organism at the Arctic, imagine if all of its phospholipids are saturated. Is there going to be fluidity to that membrane? No. So a way to increase fluidity or a way to increase permeability is give some spacing between those phospholipids. In other words, increase the percentage of cis unsaturated fatty acids in that plasma membrane. On the other hand, the microorganism in Cuba, if it's got cis unsaturated fatty acids in its membrane, they're going to be moving all over the place. That means that you've got oxygen, or you've probably got gases diffusing through the membrane quicker than they should be. You've probably got some molecules that shouldn't just be passing through the membrane that are. And so how does a cell deal with that? How does it reduce its permeability? Pack them tighter together. Increase that concentration of saturated fatty acids. Why practice this question? This has actually...
What's the answer?
So
Right.
you tell me. So which one has higher cis? Good. Because to maintain that consistent amount of consistent amount of permeability, it has to create some spacing between those phospholipids. So to do so,